Imagine you are talking to your favorite AI assistant and it's answering millions of questions every second. But what if the assistant behind it couldn't move data fast enough? Everything would slow down. Response would lag. The experience would feel broken. This is exactly why ultra-high-speed Serdes exists. Serdes stands for serializer and deserializer. It's a circuit that moves huge amounts of data super quickly inside AI servers. Think of it like a nervous system that connects all the processors together. Without fast Serdes, AI cannot think or respond in real time. As AI gets bigger and smarter, the need for speed grows even faster. We are not talking about a little speed boost here. We are talking about hitting 200 gigabits per second and beyond. This is the race to keep AI ahead of the game. So today, I want to show you what ultra high-speed Serdes is, why AI depends on it, and how we actually design, debug, and verify these incredibly fast systems. Imagine a massive highway with millions of cars flying down the road every second. Ultra high-speed Serdes is just like that, except with the data inside chips. It takes wide, slow-moving data and squeezes it into a narrow, high-speed lanes. The serializer packs the data tight. The deserializer unpacks it when it arrives. We do this because the wide road takes up too much space on a chip. So instead, we build super fast single-lane highway that push data at incredible speed. Today's Serdes can hit speeds like 112 gigabits per second, 224 gigabits per second, and more. But here's the problem. At these speeds, signals weaken, jitter grows, and noise becomes a serious threat. Serdes has to be smart enough to correct mistakes and adapt on the fly. It's like driving a Formula One car while constantly adjusting the steering to stay on the track. And inside AI servers, we are building thousands of these high-speed lanes working together at the same time. Without Serdes, nothing moves. AI systems will just sit there waiting, doing nothing. Ultra high-speed Serdes is what keeps them alive. AI is everywhere now. Self-driving cars, chatbots, medical imaging, and way more. But behind the scenes, it's powered by massive cluster of GPUs all working together like a huge team. And teams only work if they can communicate fast and clearly. AI trainings moves unbelievable amounts of data between GPUs nonstop. If any part of that flow slows down, the whole system falls apart. Think of AI like an orchestra. Serdes is the conductor, making sure everyone stays perfect in sync. If Serdes slows down, the whole performance collapses. And the bigger AI models get, the more pressure there's to keep the data moving. We need super low latency, so there's no waiting. Huge bandwidth, so we can send more data. And low power, so the system doesn't overheat. And somehow, we have to balance all three at once. This is the challenge that keeps Serdes designers busy. AI cannot keep growing without Serdes keep the pace. At these ultra high speeds, everything becomes a problem. The longer the wire, the weaker the signal. noise sneaks into the line. Crosstalk from nearby signals cause interference. Jitter throw off the timing. Imagine, once bring across a stadium and expect someone on the other side to understand you perfectly. That's what it's like trying to send a 200 gigabit per second signal over a long connection. Total signal loss can hit extreme levels, and reflection from connectors and via bounce back into the system, causing confusion. We are pushing the limits of physics just to make that work. Every part of the system, from circuit board to the package to the cables, becomes a battleground where we fight for signal quality. We cannot just make signals stronger. We have to make them smarter with adaptive equalization, cloud recovery, and constant calibration. It's like balancing on a tightrope during a hurricane. That's why debugging and verifying Serdes design is so critical. Designing ultra-high-speed Serdes starts by understanding the backfield. First, we model the entire data path. The wires, the losses, the interference. Then we pick the right tool for the job. Maybe it's a kernel driver, or a continuous time linear equalizer, or a decision feedback equalizer. We need powerful clock recovery circuits to keep everything synchronized, and delay line to fight jitter. We add equalization to clean up the signal before and after transmission. Once the architecture is set, we simulate everything over and over again. We check power, we check speed, we check area, we check signal integrity. Every choice we make affects performance everywhere. Designing Serdes is like solving a 3D puzzle where blindfolded. But when it all comes together and you finally see those clean eye diagrams, it's worth every bit of effort. Debugging ultra-high-speed Serdes is nothing like debugging regular circuits. You cannot just hook up a scope and hope the best. We have to measure every tiny details of the signal. We look at eye diagram to see how open or closed the signal is. We check jitter and noise. We check down reflection and loss. If the eye is closing, we check pre-tap. If the jitter is too high, we check the clock circuits. Sometimes we intentionally inject errors and see how the system handles failures. Debugging happens in both simulation and Unreal hardware. High-speed scopes, big array testers, and oscilloscopes become your best friend. Logs and automation scripts help us hack down invisible problems. Every bug is like a mystery, and finding the cause feels like cracking a secret code. There's always something new to discover. Verification is the last line to defense before the system goes out into real world. We check every detail to make sure the Serdes meets industry standards. We test it at different temperatures, different speed, different voltages. We see how it holds up after years of use. We throw worst-case conditions at it. Voltage swings, temperature spikes, noise, and more. We check how many bit errors happens across millions or billions of transmitted bits. We make sure the Serdes pairs nicely with other devices on the same network with similar endless amounts of data to make sure nothing breaks. And we check power, signal integrity, and margin the whole way through. Verification takes time, patience, and serious attention to detail. Passing this test means you are ready for the real world. AI is changing everywhere, everything, and Serdes is making that possible. If you want to work the most cutting-edge technology, this is it. Serdes is the nervous system of data. Understanding it puts you right in the middle of action. These skills open doors to careers in AI hardware, cloud data centers, high-speed networking, and beyond. It's some of the fastest, most complex, and honestly, most fun engineering work you can do. You get to solve problems no one else has cracked yet. You can build systems running at hundreds of gigabits per second and say, yeah, I designed that. If you like solving hardware problems and pushing the limits, Serdes is exactly where you want to be. Start with the basics. Learn how signals behave. Study pairs, equation, and color recovery. Get comfortable reading eye diagram and jitter measurement. Try simulating simple links to see what happens. Look up standards like PCIe, Ethernet, and USB to see real-world examples. Find mentors who can show you the ropes. If you can, get hands-on experience with test equipment, and most importantly, keep asking questions. Why does this work? Why does it not work? Serdes rewards curiosity and persistence. The more you dig in, the more it opens up. Here are the summarized images showing you why ultra-high-speed Serdes is what keeps AI moving. It solves impossible problems every day, so AI can keep growing. Without it, we wouldn't have the powerful system we rely on today. And as data demands keep rising, Serdes only becomes more important. Whether you want to design these systems, debug them, or just understand how they work, now is the time to get involved. So, if you are excited about building the future of high-speed data, join us. Start learning, start experimenting, and see how far you can go. Thanks for watching. Before you go, if you are benefiting from those circuit images, I would love to hear your feedback. And please share your comments down below. Lastly, please share the video link with people who may be benefit from it.